Well, now let's enjoy another presentation, which I'm sure there's been already enough hype prepared for it, because we've heard SpiNNcloud 1, SpiNNcloud 2 just been mentioned, and then the name of Christian already been here. So I don't know what actually happened there lately so much about work in Dresden on SpiNNcloud, and we're yet to hear from Christian. Christian,
cool.
Very welcome, please.
Right, thanks. So let me continue actually where Andrew left off. So we need a bigger computer, right? I'm going to argue we need a range of bigger computers, right? So SpiNNcloud 2, and now we're going towards SpiNNcloud 3. So yeah, I'm going to give you a bit of a take on that. So it also kind of breaks slightly with the other talks here, because we've seen a lot of talks about the past. This will, of course, also be about the past, about this journey. But yeah, as I'm kind of lowering the age limit in here, I think a little bit, I'm also going to talk about the future. So where do we take this machine? Does this work? Come on. The lower one. Okay, thanks. For those of you who don't know me, so we're based in Dresden at the electric engineering faculty, and I head up a group that's about 40, 45 people, mostly coming from a circuit design perspective. So we're kind of bottom-up engineers, where Steve is top-down, coming from the architecture. We come from the transistor and work upwards towards processor systems, for example, or AI systems, neuromorphic systems, or neural implants. So we're pretty interdisciplinary, so I've also got algorithm people on my payroll. So of course we need to kind of do hardware software co-design, adapt the algorithms to the machine, and actually have even medical doctors on my payroll for the neural implants. We've got our kind of what I call our biotope spin-offs, 4 companies, about 250 people. So we're very closely knit, right? People drift around from the chair to the startups, back again, or people at the chair kind of do this, have segment shops in the startups. So we've got a huge IP base. We've got a huge manpower that we can actually apply to projects like that. I don't think I could have done SpiNNcloud 2 together with Manchester if I didn't have this background behind me, right? We had this direct connection to global foundries locally. We could run short loop wafers, really adapt the technology to the architecture and vice versa. So it was a really fun journey. Yeah, so this is what we do. We very much focus on the systems on chips. So where other academic groups focus on, let's say, just the ID conversion, just the NOCs, etc., we do all of those, but we subsume it. So we always think from a system perspective. We do that quite often. Does this? Yeah, actually works. No, hardly see it. Anyways, so you can see on the right-hand side about 3 to 4 tape-outs per year. Yeah, and we actually cover something like 14 orders of magnitude. So especially SpiNNcloud 2, if you count the individual transistors, this is 10 to the 14 transistors, which of course we didn't touch individually, each single one, but there are actually transistors that are mixed signal designed in the interconnects, in the power management, for example. So there's really full custom design also gone into there. Yeah, nobody expects Saxony to actually be the 5th largest ICT location in the world. So we produce 36% of European chips, and actually, of course, with TSMC fab now coming here, Infineon enlarging, Bosch enlarging, Intel just being 1.5 hours drive away, this region is really going towards the future. Slight anecdote here. Where does it all come from? So Dresden was one of the 3 main locations of the semiconductor industry in East German times. And that, of course, meant re-engineering. So my old boss tells stories about microwaxes and other types of processes that they basically scrubbed off, did the re-engineering of the interconnects. And fun fact here is, after reunification, after the Iron Curtain came down, actually the Americans came in and tried to sue them for patent infringement. But the point is, when they re-engineered it, they actually found bugs in the original microcode. So they fixed those, and that was counted as enough of their own kind of scientific contribution that they didn't infringe on the patents. So this is what we live out of, right? We had this manpower, and then some clever industry politics came in, which led towards Saxony really developing along those lines. Okay, so yeah, okay, I call this the life of Brian. No, it's the life of the brain, aka SpiNNcloud 1, 2, 3. And it starts, of course, with Manchester. So I'm not going, as I said, I'm not going too far back in history. 20 years is enough. Kind of the starting point where Steve got started on SpiNNcloud. We got started actually on the BrainScale system, or what was back then the Facet system, 2004, respectively 2005. So this is where both of us, I call this the asynchronous phase, right? We didn't yet meet up, but we kind of kept building our competences, right? And on Manchester side, of course, we all heard it. You had the AMOLED designs, various ARM processors. In Dresden side, we did neuromorphic image sensors. We did all kinds of digital analog signal processing. So we're building up that competency. Also kind of like it is with Alex, in the sense this was an East-West meetup, right? Way after Iron Curtain came down, but still it's kind of matching those competences. Okay, so yeah, timeline more. Bear with me, this slide is gonna be pretty crowded until I'm through with it. 2009, we had the SpiNNcloud 1 chip tape out. 2008, so we were handling in the BrainScale system the off-wafer communication. We had the final tape out of that chip, 2008. Sorry, it's one too much, but anyways. 2012, the 48-node SpiNNcloud 1 board becomes available. We also started in 2012 going towards multiprocessor systems. So this Tomahawk 2 was a software-defined radio platform, 16 processors. And then 2013, so in this run-up phase to the Human Brain Project, or in the late phase of the BrainScales project, Steve and us met up, and it was like, okay, we do processor systems bottom up, he does processor systems top down. So after one famous meeting in Manchester, we kind of concluded, yes, let's do this together, SpiNNcloud 2. And I'm definitely very grateful to Steve that we had this opportunity to kind of really show what we could do in this joint project. First prototype for SpiNNcloud 2 was 2015, and then of course Brexit happened, but two small villages of indomitable Saxons and Anglo-Saxons keep cooperating. So yes, it got, I mean, 2016, nothing much happened, but it gets progressively harder actually to cooperate, right? To find joint projects across the channel, unfortunately. Right, actually phase 2017 to 19 was pretty decisive in a number of ways. Human Brain Project took the decision of canceling SpiNNcloud 2. Essentially, Human Brain Project management told us we already have a SpiNNcloud there, we don't need a second generation. So they pretty much kicked us out. Before I did have 6 positions in Dresden, afterwards I had half a position. So yeah, it was a token. So I had to find local funding. It was also kind of fun that the EU reviewers we had for the Human Brain Project, they told us about SpiNNcloud 2, where are the memristors? You don't have enough memristors in there. Which was kind of fun when I then applied for SpiNNcloud 2 funding in the federal German level. They also told us, yeah, for this funding instrument, you need more memristors in the machine, so you don't get it. But the local Saxon guys were very interested in kind of showcasing what the Saxon environment could be doing. So we got the local funding, actually these days is in excess of 15 million. We did a technology switch, so we went to this back then very new 22 FDX, FDSOI technology. I'm going to show you later what that gives us. We also made a decision to hybridize SpiNNcloud 2. So it's not a purely spiking system anymore, right? It has DNNs in there. It has probabilistic computing in there. So kind of opens up SpiNNcloud 2 for a lot more use cases. And of course, also in the same time frame, the big SpiNNcloud 1 machine became operational. Right, so then 2021, we had the final SpiNNcloud 2 tape out. Also SpiNNcloud Systems was founded, so we are commercializing the chip big time. And August, September last year, the first 48 node boards, SpiNNcloud 2, became available. And this year we're building up a 5 million core machine, so half-sized so far. 2025 we built it up to full size. And this year, actually in April, we will start serious work on SpiNNcloud 3 design. So we have the funding approved. Right, so what is SpiNNcloud 2 about? First of all, it's kind of just scaling up. So factor 10x, actually scaling is more like a factor 30, 40. Think of it as compressing one of the old boards inside a single chip. We went much more kind of event-based compute. So each core this dynamic power management, basically runs the cores, runs the memory, and even the communication links. They're all energy proportional, event-based in the sense that we only draw power if we do something with the machine. As I said, it's a hybrid thing, so it's got multiple accumulate accelerators. It has neuromorphic accelerators, right? It's not entirely software-based as SpiNNcloud 1. For certain numeric operations, we just offload the stuff. So the ARM core is kind of a more a management core these days, where we do the general purpose compute and the rest we offload. Can I go back? Yeah. What's also maybe interesting, that's a special feature of the FDSI technology, so we put in adaptive body biasing. This is some know-how one of our startups contributed. This is at runtime. So we basically, everything that's temperature-related deviations that's across the transistors, everything that's manufacturing, everything that's aging, we basically cancel them out at runtime, which essentially means, you can see it up there, we run down to 450 millivolts. If you compare that to a 3 nanometer technology, that still is around 700 millivolt. So just by kind of, I think of it as in a biological sense, it's like a homeostasis mechanism. And this homeostasis allows us to go very much towards the minimum energy point of that system. So we're actually competitive to a lot of the kind of GPUs and smaller technologies. Right, and it's been, yeah, I totally appreciate, Steve, the problems you had in Manchester in setting up the machine. This has been one hell of a management job, and I'm not sure I actually would have done it if I had known what I was getting into. I was telling Steve an anecdote. When we first started talking to university management, yeah, I want to set up that machine. First question was rooms. Okay, so we're talking to the rooms people. Second question was, we need to talk to the university compute people. Third question was, yeah, water cooling is not going to be available in the room, so we need to talk to the construction people. Then we started talking to the fire people. Then we started talking to the work security people. So I had to get bigger and bigger meeting rooms until I was, after half a year, meetings kept getting bigger on a kind of weekly basis. I was like, do I finally have everybody in this university who's concerned with some aspect of that machine at the same table? It was hilarious. And every new guy or lady who comes in was like, why haven't you told me a month ago? I need to be involved in this. So they had to throw their weight around first. And then we were all like, yes, we should have. And then they were fine. Anyway, so development cost, I figure about 30 million. Deployment cost, 10 million. And we were coordinating almost 100-person design team. So that's the machine in Dresden, the half-sized one, 8 racks. That's still empty, of course. What they call in East Germany, it's a Potemkinsches Dorf. So we still need to fill it with the boards. Quite some sizable numbers. So we can support AI or some other optimization or, of course, spiking neural network models up to 10 to the 14 parameters. So it's getting towards brain size. And we do that at real time. So the Mac accelerators can deliver 10 to the 14 synaptic operations per millisecond, right? So again, this is one aspect, of course, we took over from SpiNNcloud 1 time models itself. So we don't do synchronization. We are synchronous at the local level in the core, but we are asynchronous globally. So that's also the algorithms we designed for it. And yes, so we do crazy stuff on it. You can hybridize it. You can put symbolic AI on top of a DNN, even have the lower layers SNN. You can be all over the place in terms of the models you do, or have some SNN and have a meta layer on top where you're adapting the learning rules, for example, to do very efficient learning. So all crazy kinds of stuff. So again, a little bit like the slides we already had seen for SpiNNcloud 1. So we're branching out into quite a number of applications. So a lot of real-time AI, so we're hybridizing kind of RNNs, DNNs in an event-based fashion with SNNs. So that's, for example, upper right here, this event-based gated recurrent unit. We, of course, do the classic stuff, kind of neuroscience emulation. We do drug discovery, we do optimization, same fashion as the Louis people do it, and about 4 other applications at the moment. A lot of them also driven commercially by the startup. Okay, so kind of finish off a little bit, some impressions of this journey. So upper left, that's Katrin Amunds, who heads up the Human Brain Project these days, or headed up. Human Brain is, of course, over since September last year. And that's the 3 of us standing in Dresden for the press. We had just gotten the local Saxon financing for the SpiNNcloud 2 machine. And lower right, that was me. So we had Steve over when he had his 64th birthday. So it's a nice binary number. And I went to the local, what's conditor in English? Guys doing the cakes. Anyways, and went with them with a picture of a SpiNNcloud 1 board, and they printed it on eatable paper, basically, so we could put it on the cake. Right, so upper right, that's me and Steve doing advertisement videos for SpiNNcloud Systems for the new company. So we were, with these big markers, writing on a piece of glass and were filmed from the backside. Look very fancy. And of course, we had plenty of SpiNNcloud 2 brainstorming sessions. So we invited Steve over to Swiss Saxony, went hiking. Yeah, did the same in Manchester. So there was quite a number of neat brainstorming sessions. Okay, a bit more anecdotes. Navigating the Human Brain Project. That is a fun one. That was the old structure. You had 3 directors. Basically, you knew where you had to go to for if you had any kind of problem, if you needed funding, whatever. That was a clean structure, right? But then, of course, EU stepped in, started micromanaging. They weren't satisfied with Henry Markram's style of things. And I call this the Ministry of Silly Talks. This is the new structure, right? Management by board. And it hardly mattered which board you talked to. None of them was responsive, and none of them took any decisions, at least not that I could notice. So I hardly knew how to navigate this thing anymore. So yeah, that's the Human Brain Project. We had a lot of fun with HPP acronyms. So actually, the late Karl-Heinz Meyer did an HPP dictionary once because there were just all kinds of acronyms all over the place. HPP funding intervals was also fun, right? It's not a 10-year project. It was sliced up into real separate projects, 2 years each. So doing the prototype chips, for example, was very much planning around those. Do we still have money left, or do we have money in the new project? So that made for some chip scheduling that wasn't really driven from a technical perspective, but more from a financing perspective, which isn't ideally how you would do a project. Also, of course, Steve can tell the same story. Funding was delayed. So a lot of times the start of the new funding period was delayed. So we somehow had to keep rescuing people across half years of unfunding. Yeah, of course. And finding out what's really going on. The interesting part is this visual cortex, right? So I figure someone at the EU reviewer level who instigated that structure on top of us was like, yeah, we're figuring out the brain in that project, so we need a management structure that's about as complex. Right. Okay, some random quotes. Consistency is more important than truth. That's Steve on project proposal writing. Or Steve also, how many ARM cores do we have this week? Because that kept kind of changing across our brainstorming sessions, according to how much we put in there, how much area the place and route took. So we had everything, I think, from 130 to 170 cores. It kept changing. Yeah, any document that mentions the word quantum together with neuromorphics immediately loses all credibility. Fun fact, of course, Heidelberg now has a chair on neuromorphic quantum photonics. We had new financial units in the Human Brain Project. 1 Markram is 1 billion euro. Yeah, and those are some other, the quotes on SpiNNcloud 2 already did. Karl-Heinz Meyer, dual use would imply we already have multiple use cases for neuromorphic hardware. In fact, we're struggling with the first use. Or I put in ChatGPT, we're sure Steve's retirement will be anything but idle. Of course, unless of course he's experimented with low power modes in his hammer. Here's to retirement filled with armchairs, cashing in on life's pleasures and branching out into new architectures. ChatGPT has a sense of humor, right? Okay, so coming towards the end of my talk. Yeah, SpiNNcloud story continues. And there's actually 3 teams involved these days, right? There is Manchester still continuing. There is my group in Dresden. And then there's SpiNNcloud Systems, which is basically hiring someone new every week. So this team, that's the state of last September about. Team has already grown by 10 more people. So there is some dynamic behind that. And then, of course, John actually noticed that this is a way old picture for John. But I didn't have a more up-to-date one. But let's see how that continues in Manchester. I'm looking forward to that. That's the roadmap, right? We're seriously working towards SpiNNcloud 3, which will be kind of getting in all our learnings we now have from the architecture perspective, because as I said, especially on the Dresden side, we very much come from the chip level. And we're also going towards more an event-based general compute machine. That's essentially what we're going to build. There's a lot of early SpiNNcloud 2 adapters already for a system that's barely out of the crib, so to speak. Yeah, lots of the German stuff, international universities, companies. So we've got SpiNNcloud running around in the BMW, etc., etc. So we actually use it in teaching already, and there is startups forming around it for drug discovery, then of course SpiNNcloud Systems. So that's pretty cool. And yeah, to loosely quote Andrew, now feel free to throw rocks at me.